Hi, this is Professor Stugard, and today we're going to be talking about how we visualize and think about three-dimensional space. Multivariable calculus, aka Calc 3, most of the time we're going to be working in three dimensions. Now we will spend some time in two dimensions, and almost everything that we do in Calc 3 can actually be extended into higher dimensions, four dimensions, or as many dimensions as you want, but to still have a firm grasp in understanding these concepts the first time around, it's good to be able to visualize them and see them on paper. Again, most of these tools that we use in calculus, like integrals, well, an integral just means add up a bunch of things. And it's really nice to do that in context of something physical. And so again, we're going to be doing most of our work in this 3D space and looking at things in three dimensions, even though we'll be able to build off these ideas into as many dimensions as we want. Now, to go back to the three dimensions, well, we basically start with our typical two-dimensional space, which is our XY coordinate system, and we need to add an extra dimension of freedom or an extra degree of movement, and so, well, the obvious choice is to choose Z, which means that every point in space is going to be an ordered triple now, X, Y, Z. Triple because now, again, there's three dimensions, and now order matters. That's why it's called ordered triple or an ordered pair, and of course that order is alphabetical. Now, what we have here is a little bit of set notation. Again, we can tell it's set notation because we see our braces, our squiggly brackets, and again, our point in space, we still use parentheses to denote the point in space. And if you're unfamiliar with that set notation, we're saying that every point in space with an X, Y, and Z, that vertical line here means the rule is, and then X, Y, and Z are all elements of the real numbers, which means everything we're going to be dealing with in Calc 3 is going to be in the real numbers. No complex numbers for us in Calc 3. Again, a little piece of notation. This E looking thing here, that is the formal set notation way that we say is an element of. And this chalkboard bold R, or the R kind of with the extra lines, stands for the real numbers. Now, to visualize three dimensions on two-dimensional paper or computer screens, we need to use perspective drawings and projections, which if you've done any work with drafting or you've taken some AutoCAD classes, this should feel fairly familiar. But let's talk about how we're going to actually turn two dimensions into three dimensions. So we start with our typical XY plane, and what we're going to actually do first is just rotate it 90 degrees, just like that. Now the next step is, again, we have our XY plane kind of, well, on our screen. We want to think about laying it flat, like laying it down on our desk or the surface of a table. Kind of like that, and kind of shift our perspective to the side. And so if we have our XY plane flat on our table, the Z axis is going to come straight up. All right, it's going to be pointing directly out of your desk or out of your table. And this is typically how we're going to visualize three-dimensional space in Calc 3. The thing to remember though is, obviously I have this all labeled with my X's, my Y, and my Z. This is the way mathematicians always visualize three-dimensional space. So all of your math textbooks are always going to be set up with the X, the Y, and the Z in roughly this order. However, that's not always the case for all of physics or all of engineering. So always make sure that you're taking a lot of time and make sure you understand what's going on first before you try to, do any math or start writing down symbols furiously on your piece of paper. Make sure you've identified exactly where your X, Y, and Z are going to be. Again, in Calc 3, we're going to be consistent and always set it up this way, but that's not always the case in other texts or in other examples. Now, if I want to plot my point, X, Y, Z, in 3D space, here's how we're going to do it. First, that XY plane that we had laid down flat on our desk, but rotated 90 degrees, we want to find the point XY on that plane surface, on that flat piece of paper. And then what we want to think about, or again, how we want to really interpret these points we're going to consider z to be the height. All right. So again, once you find your point in the xy plane, which is kind of flat on your desk, we're going to basically go directly up from that point, however many units z is, and that gives us our point in space. All right. So again, typically find the xy coordinates first, and then z is going to be your height. And again, that's how we're actually going to think about pretty much everything in 3D space when we eventually get to chapter 14, well, which is actually going to happen sooner than you probably think. Now, 3D space. This is commonly referred to as, well, 3 space, and that's typically how I'm going to refer to it, as 3 space. Although we frequently also use the notation R3, and again, meaning that we have the real numbers, right, that symbol for real numbers, and 3 as my exponent means it's in 3 dimensions. And typically, again, we're only going to draw the positive values of our axes in 3D space, but they do extend infinitely in the negative directions, and we would draw them as necessary. And so this image over here, we can see we still have the x, the y, and the z in relatively the same spots, although again, it is tilted a little bit. And this image is from your book. And again, sometimes they will rotate it just slightly, but it's still in roughly the same orientation. And you can see they started drawing the negative axes as well. They started drawing these negative values just, well, to help you kind of visualize what's going on, since we're going to skip it most of the time. Now, our 3 coordinate axes, the x-axis, the y-axis, and the z-axis, are going to divide 3D space into octants, meaning 8 different regions. And if you're having a hard time visualizing this, literally just grab 3 pencils and hold them all at 3 right angles to each other, and you can kind of see how they each, well, they're going to basically subdivide space into 8 different, well, octants in this case. When we refer to the first octant, that's going to be the values where x, y, and z are all positive. And that's really the only one you need to worry about. I know in the 2D planes, quadrants, right? When we have 2 axes, it divides our plane into quadrants. So there's 1, 2, 3, 4, and we go around counterclockwise. You don't have to worry about numbering them except for the first octant. The first octant is just where they're all going to be positive. Now we're going to take a look at surfaces in 3 space. Eventually we will get to lines and curves and those other things, but we're going to start with surfaces. And we're going to start with the simplest surface, which is a plane. And a plane is just a flat 2-dimensional surface that extends infinitely. So essentially, it's like having a piece of paper that you're holding up in space that just goes out, well, infinitely in all directions. Now, if we have a plane that's defined by 2 coordinate axes, we call that a coordinate plane. And all planes can be written in this form down here, where x, y, and z are your variables, and then a, b, c, and d are in the real numbers. Now, the way I know that this is going to be a plane is that my x, my y, and my z are all linear. This is a linear function because there are no exponents with my there's no exponents with my x, my y, or my z. All right. If there was an exponent, if there was an x squared or a y squared, it would no longer be a plane. But as long as we have x, y's, and z's, and they're all just to the first power, then, well, it's got to be a plane surface. So let's take a look at a simple plane surface. And this is going to be the surface given by z equals 4. So this surface is the set of all points with a z coordinate of 4. Again, it's as straightforward as it sounds and looks. And that's going to be true for all x and y. So we have down here, again, our set notation, where, again, we have our ordered triple, x, y, and, well, z, except now we know that z has got to be 4. All right. And when we look at this, again, what this is saying is that every z coordinate must be 4. So if we're thinking about this in terms of what we did before, if I find a point in my xy plane, let's say that point there, if I go up 4 units, well, that's going to be where the plane z equals 4 is. And even if I choose a different point, like one over here, if I go up 4 units, it's going to hit that plane z equals 4. So it'll be that constant height. So again, if you have your xy plane on your desk, like I said before, then z equals 4 is just going to be a piece of paper almost parallel to your desk. or perpendicular to the z-axis that extends infinitely. Now, when we try to visualize more complicated surfaces in 3 space, this can actually be incredibly challenging. So to assist, what we want to do is look at the projections that these surfaces make into each of our coordinate planes. So again, I said earlier that if you've done some drafting before or worked with AutoCAD, well, when we do drafting or engineering really of any kind, when we come up with our engineering specs, we do, well, what's the view from head on, what's the view from the side, what's the view from the top, and we kind of combine them together into our, well, kind of projective visualization in 3 space. We want to do the same thing in math, is try to look at these projections into our coordinate planes. And so to do a projection into a 2D plane, right, trying to convert essentially our 3-dimensional surface into a 2-dimensional image, what we do is we take the missing variable from each coordinate plane and set it equal to 0. Now let's take a look at this by actually doing an example. So let's say I want to investigate the surface given by x plus z equals 1. Now the thing is, I already know that this has got to be a plane because when I look at my equation, well, it's linear. There's no exponents. It's x to the first and z to the first. There's no squares or cubes or anything else. And that means it's got to be a plane. And my coefficients are all 1, so again, fairly simple. Now, if I want to look at the projection of this into my xy plane, well, again, my numbers are x, y, and z. So if it's in the xy plane, the missing variable here is z. So we're going to set z equal to 0 into our original equation. So if I plug 0 in for z, well, again, this is very simple. We just get x equals 1. And then we would sketch in the xy plane, well, x equals 1. And again, notice how everything is labeled, right? I labeled my axes, my x-axis and my y-axis, and then x equals 1 is just a vertical line at, well, x equals 1. Now we need to look into our other 2 coordinate axes, or other 2 coordinate planes. And so we'll now do the yz plane. So if I'm looking in the yz plane, my missing variable now is x equals 0. That's what we want to plug in. So if I plug in 0, well, now I get z equals 1. And again, pretty straightforward. So now I'm plotting in the YZ plane. Now, typically when we do our projection in the YZ plane, Y now becomes our horizontal axis and Z is now our vertical axis. So again, pay attention to how everything's labeled. And then if Z equals 1, well, that's just going to be now a horizontal line at, well, Z equals 1. And lastly, my last coordinate plane is going to be the xz plane, which is where we get rid of the variable y. So plug 0 in everywhere I see y, except, well, there are no y's. So it's just going to be x plus z equals 1. So, okay, x plus z equals 1, but I'm doing this now in my xz plane. And again, x is still my horizontal axis. Z is going to be my vertical axis, and that's exactly what the line looks like. And if you need to find the intercepts, that's fine. Again, however you need to, figure out how to plot that line on your own, that's fine. But we can see it's clearly this line with a slope of -1, and that's what it looks like. And now we can try to combine all of these ideas together, sketch them on my 3D surface, and see what it is that, well, I'm going to get.
So here we can see that last graph now. And so I'm using GeoGebra. They have a really nice 3D grapher, and you can absolutely use that too. It's online. Just, search for GeoGebra 3D grapher. And you can see up here over by the equation, I've typed in my x plus z equals 1, and we kind of see that last line, the projection in the xz plane. This is exactly what it looks like. Now what happens though is that this is a 3D grapher, and actually as I start to rotate, we can see that this is actually going to be a plane surface. And a plane is basically, think like a sheet of paper that extends to infinity in every direction. And where that plane is, again, that really helps me understand what's going on with this particular function. And we can see that were I to kind of switch it up here, we can see that, oh yeah, look, there's my line on that right-hand side where it intersects at 1. Or if I look at my other projections, um, we can see where it's intersecting there as well at 1. And again, by combining those 3 different projections, we can hopefully get an idea of what's going on in this function, and it will actually help us as we're setting up more calculus-related things to do a little later.
So now let's kind of change directions a little bit and talk about another really important concept, which is, well, measuring distances. How far are two things apart from each other in space? Now, as I'm going to do a lot, I'd like to start in 2 dimensions and then see how we build to 3 dimensions. So in R2, or again, 2 dimensions, when we find the distance between any 2 points in space, let's say P1 and P2, we're just using the Pythagorean theorem. So if the distance is d, then the distance between P1 and P2, and again, here's the notation for that. Now notice how we have those vertical lines, kind of like we're doing absolute values, because, well, yeah, we are. Absolute values are just a measure of distance. When we do the absolute value of a number, we're asking, well, how far is that number from 0? And when we use that notation, now for 2 different points, we're asking how far apart are these 2 points. Those absolute values always mean our distance. And again, we're just doing the Pythagorean theorem. The difference in the x-coordinate squared plus the difference in the y-coordinate squared, and take the whole square root. And yeah, it's just a bunch of right triangle trig. If we actually did this out and drew a picture with our 2 points x1, y1, and x2, y2, if I want to find that distance d between them, we just make a right triangle. And the legs of these triangles will be the absolute value of the difference of the position, which is also the distances between them. And again, we're just really just setting up the Pythagorean theorem. In fact, so much of what we do in Calculus 3 is just going to be applying right triangle trig to everything. Hopefully you've brushed up on that pretty well. And so that whole formula is really just the Pythagorean theorem written out to look a little bit more confusing. The nice part is, when we're in 3 dimensions or in R3, even if we have an extra coordinate, well, we're still using the Pythagorean theorem. We're just using the 3D version of the Pythagorean theorem. That distance d, and again, regardless of dimensions, my notation is still the same with the absolute values. We take the distance between the x-coordinate squared, the difference between the y-coordinate squared, the difference between the z-coordinate squared, add those all up, take the square root, and yeah, we're just applying the Pythagorean theorem, but in 3 dimensions, which is quite convenient. Now, when we're talking about objects that have constant distances, again, hopefully this seems familiar, and you remember all of this from doing basics of conic sections, or even earlier than that. But in 2 dimensions, the set of all points whose distance away from some given point is a constant, in this case the constant r, standing for radius, well, that's our circle. And here's our equation of a circle with a center of AB and, well, a radius of r. And that should be a very familiar formula for you. And if not, well, brush up just a little bit because these things will be coming back again. And the nice part is, well, when we build up to 3 dimensions, it's the same exact idea. In R3, the set of all points whose distance away from some center point is a constant r, again, a radius, is now a sphere. Right? In 2 dimensions, it's a circle. In 3 dimensions, it's a sphere. And it's the exact same formula. And this is the one that your book gives as well. And it's, well, really just making sure we understand how these formulas work and distances. And again, it's all just applying the Pythagorean theorem, just in different dimensional spaces. So let's finish up this lecture with a quick example. How would I show that this equation is the equation of a sphere? Well, first of all, I know it's not a plane surface because, well, look at that. I have exponents. Can't be a plane, can it? But my exponents are all squares. Square, square, and square, which probably means I am dealing with a sphere. But how would I actually show that? How would I prove it? Well, this is actually trying to help you with one of your homework questions. The first thing I want to do is actually set it to 0 and then group by the variables. So let's move everything over to that left-hand side. And when I group, so the x squared, well, there's only one term with x's, and that's the x squared. But when I group the y's, so I'd have y squared, and I had to subtract the 14y from both sides. And then with the z, I had to add that 6z to both sides. So again, I'm grouping inside my parentheses. Now to show that this is an equation of a sphere, I'm going to have to complete the square for each variable. All right, now completing the square means, well, in this case, what do I need to add? What constant term do I need to add to make each of these a perfect square trinomial that I can factor? Now, hopefully we remember how to complete the square. I know it showed up in some of your integration techniques, hopefully, and hopefully this is ingrained, but if not, I know it happens. We can't possibly be expected to remember everything. We use the b divided by 2a and then the quantity squared. So for example, for my y term, we take the b, which is 14, divided by 2a. Well, a is just 1 in this case, right? That invisible 1 in front of my coefficient. So half of negative 14 is negative 7. Squaring negative 7 gives me 49. And so when we complete the square, we had 49 for the y terms. And for the z terms, well, half of 6 is 3. 3 squared is 9. So add 9. And just be really, really careful. You have to balance the equation. You can't just add numbers on one side and not add them to the other. This is still an equation with an equal sign. Make sure everything stays balanced. Well, now that we completed the square, all that's left to do is to factor it into our perfect square trinomials. And hopefully that should be pretty easy. And so the x term, again, it was just x squared. So I'm writing out x minus 0. You don't really have to do that, but it's going to help me describe my circle. Obviously, the y terms become y minus 7 quantity squared, and the z terms were z plus 3 quantity squared. And on the other side, that 49 plus 9 gave me 58, which means I can now describe exactly what this sphere is in space going back. So the center of the sphere is going to be at 0, because minus 0, 7, because minus 7, negative 3, because it's going to be minus that 3. Remember, it's always that opposite, right? That's how we set it up. So the center of the sphere is 0, 7, negative 3, and my radius is the square root of 58. That is a very, very common mistake. We get to this end, remember that last one at the end equals r squared. So if I want my actual radius, well, I have to take the square root. And that's how we can prove that this is the equation of a sphere. So this wraps up our lecture on the basics of 3D space. Again, we're going to be dealing with this quite a bit during this class, so make sure you feel kind of comfortable. Absolutely take some time to play around with GeoGebra. That's one of the really, really fortunate parts about this class being online, is that everybody can take as much time as they want. They can go to GeoGebra and actually graph these. Let technology do some of this hard work for you. Spin them around, look at them, try to understand what's going on before you actually, start throwing math on your paper. If you have any questions, please feel free to email me, and good luck.